Our goal in this work is to compute a sequence of approximate derivatives of a computable function as quickly and accurately as possible. In practice, our work will likely be most useful for optimization scenarios in robotics or related areas where a sequence of derivatives are commonly used to guide an iterative process to find local or global minima of a function. In this work, we propose accelerating derivative computation primarily by reusing information from previous, related calculations, a general strategy known as coherence. We will now provide a brief explanation of our technical ideas. To start, let's think about how a derivative matrix can map a matrix of tangents, labeled as delta x, to a matrix of Jacobian vector products, labeled as delta f. Each column in the delta x matrix is an individual tangent vector labeled as delta x sub I, and each column in the delta f matrix is a corresponding Jacobian vector product, labeled as delta f sub I. If we are given delta x and delta f matrices of sufficient rank and size, we can use the pseudo-inverse to solve for the derivative matrix. Let's visualize what this solution looks like. Here, the dark blue lines represent affine spaces created from corresponding columns in the delta x and delta f matrices. The Z matrices are null space basis matrices, and the Y matrices represent free variables that parameterize the affine spaces. The derivative must reside within each of these affine spaces, meaning it must lie at their intersection, as illustrated by the yellow dot in the visualization. Now, suppose we are given a new input x sub 1, and our goal is to compute a new derivative matrix at that input. This new derivative is visualized as the shifted yellow dot. Of course, one option for finding the new derivative is to use the same equation we looked at before. This would require updating all columns in the delta f matrix by computing new Jacobian vector products for all tangent directions, essentially updating all affine spaces here in order to find the new intersection point. However, computing all of these Jacobian vector products is very computationally expensive, likely requiring many calls to the original function. Instead, let's compute only a single Jacobian vector product corresponding to one tangent direction, update only the associated affine space, and leave all other Jacobian vector products and their affine spaces intersecting at the previous solution. This ensures that the true derivative must lie within the updated affine space, though its exact position remains unknown. Our key insight is that we can approximate the derivative at the current input by leveraging prior information and framing the problem as a constrained least squares optimization. The goal is to identify the point within the updated affine solution space that minimizes the Euclidean distance to the affine spaces aligned at the previous solution. In our paper, we derive the closed-form solution for this optimization using a KKT system. Additionally, we demonstrate how to precompute and cache the constant components of this solution to enhance runtime efficiency. The solution is visualized here as the green dot. This newly computed approximate derivative is subsequently used to update delta f, which is now a matrix of approximate Jacobian vector products, thus we will denote it as delta f hat. Note that with delta f hat now updated, the affine spaces all intersect at the current approximate derivative. This process iterates, cycling through the web of affine spaces, interleaving updates to the approximate derivative and delta f hat matrices for each new input in the sequence. By default, each approximate derivative only requires one Jacobian vector product to compute, regardless of how many inputs or outputs the function has. Our approach is also equipped with an error detection and correction mechanism. Thus, if at any point the approach detects that its approximate derivative is too far from the ground truth derivative, it can spend extra iterations on the current input until a certain accuracy is achieved. If all possible affine spaces are updated with ground truth Jacobian vector products at the current input, the solution will always match the ground truth. We now illustrate an example output from the second evaluation in our paper. Evaluation 2 involves using a route finding procedure to get a quadruped robot to match its feet and end effector to specified poses. we see that our WASP conditions converge much more quickly than alternative approaches. In particular, as analyses in our paper would suggest, the WASP condition with an orthonormal delta X matrix structure converges even faster and more stably. In general, the results in our paper suggest that our approach may afford significant speedups for similar applications in robotics and beyond.